Hey guys, this is the Boss Coder after a very long time, and in this video I'd like to talk about the stack some more in depth. Someone asked me a question on my stack video, and I gave them a good explanation, I think, but then after rewatching the video I realized that I was not explaining it very well, and I think that's because I didn't know as much then as I know now about the stack. So I'd like to kind of remedy that with probably a pretty lengthy video on some in-depth stuff about the stack, and I'm going to talk in some low level. This is going to be kind of like a general computing thing because this applies to pretty much any programming language out there, not just C# or any high-level languages. So let's get started. And the first thing I'd really like to talk about is the difference between temporary data versus permanent data in like the low-level parts of your computer. So as we know, this here, this int a equals 1, that's sort of your permanent data. As far as this program is concerned, in the lifetime of this program, this is kind of a permanent data. It's stored in memory, in your RAM, and it will stay there until either you are done with this method completely or until your program terminates, and it's stored in RAM. Now this piece of data, this 20 here, it's stored temporarily, and even though it just seems like a number, you might not necessarily think that it would be actually stored anywhere. It is in fact stored somewhere. Every piece of data has to be stored somewhere in your computer, and where it stores this temporary data is called a register. Now, registers are not fancy. They're simply somewhere that your computer can store temporary data, temporarily obviously, and they're not really any different than your average memory location in your RAM. The primary difference between the two is that registers are stored in your processor, and that's so that your processor can reach them very quickly and perform things like addition, subtraction, multiplication, division, and then logic operations like and, or, and not, and exclusive or too. So, that being said, what happens, that's all I have to really say about temporary data. Erase this. But temporary versus permanent data. So now what happens when we get to something like this, where it says count A? It calls this method, and it jumps down here to this block. So what happens in the computer is once it needs to save any temporary data that it was using in this code block, so that once it returns, it can continue doing its thing as though count was never actually called, because count in the background cannot modify anything that you were using in the registers in your main method, and this is kind of like a standard practice so that we can make sure that no data that we were using in a certain block of code gets corrupted even if we call another method. And it stores this data, special data, onto something called the stack. Put it in black. It would be kind of gray. On the stack. And the stack is stored, or the stack is generally kind of drawn as a graphic like this, and you allocate different memory locations to it. But you don't allocate memory locations to it, it just kind of builds up. You usually have it at the bottom, and it fills up with different things whenever you can actually put stuff on the stack manually, but whenever you're in low level, but whenever you're programming in a compiled language or whatever, it does all the placing of items and taking things off manually. And so what happens when you call this count is that once it reaches the count method, the very first thing the count method does is it pushes like all the important things onto the stack, and the stack was originally pointing here, but once you push stuff onto it, the pointer actually moves up a spot and says, okay, now here's another excuse me, here's another empty spot where I can store data. And whenever you put stuff onto the stack, so put on stack, there's a special word for this, and it's called pushing. That's literally the name. This is a key word in a lot of most assembly languages. And then, I have to erase that. And then when you take stuff off, this is called popping. You push stuff onto the stack, and you pop stuff off of the stack. So now that we kind of know how the stack works, like what exactly happens when you call a method? Well, you have like the label for the method, and then the very first thing it does is it says, okay, push any like important data, but then it also pushes something called the link register, which is link register, and I'm going to abbreviate it LR from here on out. And so what happens is it pushes this link register and any other important data. Usually the things that it pushes are kind of predefined by the compiler and whatever system you're working with. And so it pushes anything that's really important that it needs to save for when it goes back. And these things are generally predefined by the compiler or the assembler, interpreter, whatever you want to call it. Depends on what language you're working with. And so what it does is it pushes, and then it does all its code, and then it, wrong blue, and then it pops that data, pop data, and the link register, and then it jumps to link register. Put this in green. Jumps to link register. Now, what does the link register hold? When you call a method, the link register actually holds the line number of the very next statement that you need to perform when you return. So in our case, the first time we call count, the link register has this. LR has store equals line 15. So the link register kind of holds the value line 15, and then this method will pop it, and the reason, or push it, the reason you push the link register and any of the data that you need in this case is that if you call another method inside this method, you want to make sure that you sequentially save your data when it's important. Now, when you call a method, it doesn't always push and pop the data. It kind of depends on what you're doing with that data. But for most methods, you're going to want to push and pop any kind of save data, unless it's like an add thing. Then you want it to obviously modify something. But in most cases, you push the data in the link register, and then you pop the data in the link register, and then you jump to whatever line number the link register is holding, and that is a mess. So that's kind of what happens in the background whenever you compile your program or get it interpreted and turned into assembly. Now what I'd like to talk about is what happens whenever we do recursion. So I'm going to go ahead and keep this up here. Link register. Now in the case of recursion, what happens is we have count in this particular case, not every case, and then you push your data and your link register, do your stuff, but then you call yourself. Now, like I said before, whenever you even if you call another method, it still does all this pushing and stuff and putting on the stack. It's just that you can't really see the effects of it because the other method that you would be calling inside of this method is is already popping for you before returning. So it seems as though nothing actually happened whenever you return. So then you do other stuff, and then you pop the data and the link register. Oh, what did I just do? Okay. And then you jump to, what am I doing? To link register. Okay, so this is kind of, the main difference is that you're calling this. So let me erase all of this now, so I can kind of do this step by step for the first couple of iterations of this recursive thing. I'm not going to go through all 20 steps. I'm just going to do the first couple so you guys can kind of see what's going on. So we have our stack here, and we have our first location, which isn't filled yet. So now we call count A. So we pass in the variable the number 1, and it says console.writeLine A equals A on the stack. Then it goes, if A is less than 20, which it is, count A plus 1. So it actually comes back here and passes in the number 2. So the number 2 gets put on the stack. And then we come up here, and it says push that data, which is 2, and it pushes it on the stack. And there's actually should be a 1 here. Goodness gracious. Okay, so there's a 1 here, and then 2 goes here. I should actually, sorry, I need to make this really neat. I'm very OCD and compulsive. I want this to be understandable to you guys. Okay, so the first thing we did was we put 1 on the stack, but we didn't go back with the number 1. We only went back with the number 2. So then the next thing that happens is it says, is 2 less than 20? Yeah, so let's call count again with data, which is, in our case, is A plus 1. Now there's more data in here, but I'm just calling it data just because that's the only piece of data we're worried about, is this 1 number. So it passes in a 3. Now it gets to count, and it says, okay, let's push 3 and the link register on the stack again. Now is 3 less than 20? Yeah, it is. So now we're going to call count data plus 1 yet again, and we push 4. And then it keeps doing this all the way until it gets to 20. So dot, 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 etc. until it gets to 20. And so now it says, okay, it goes back and it says, okay, count, push data, which is 20, link register. Now, is 20 less than 20? No, it's not. So once we reach the 20th iteration of this recursive method, we've reached the base case, and we no longer perform this call to count. So now we have to keep doing stuff. We do the console.writeLine, and then we pop. So the first thing we pop is the number 20 and the link register. And then we jump to, actually, do we push 20? I think we do. And then we jump to the link register. Well, the link register points to, like I said before, wherever we would have been after that function call, after that method call, sorry. So the line immediately that we would have been at after this call to count A plus 1 is right here, line 23. So on the first call to our method, the link register, let me keep using green for the sake of consistency, has line 15, because we're going to return to here after we're done with, we think we're going to return there, but then it calls itself. So the 2 through 20th time, the link register actually ends up having line 23, right? Yeah, line 23 and line 15. So the first call sends in the data 1, it pushes that on the stack, and the link register of line 15, but then all the other times that we call this method, have the method call itself, it pushes the data, which is the numbers 2 through 20, and the value that the link register has, which is line 23. And so we come back down, 19, we pop the number 19, print it out, and we see that the link register is still pointing to line 23. So then we go back to line 23, pop again, write out the number 19, pop again, which brings us 18 again, and yet again the line 23. Then we jump back here, and we write out the number 18, pop 17 and the line 23 into the link register, and we do this up until we get to, it's a good color, till we get to here. And then we say, okay, let's write out the number 2, pop the data, but then when we pop the last time, we pop the number 1 for data, and then for the link register, we pop line 15. And then it says, okay, let's jump to link register, and it jumps back to line 15. I believe the program prints out the number 1. So this stuff, like I said, isn't actually literally what's happening. This is just kind of a generalization of what happens whenever your computer turns your code, your high-level language code, into like assembly code. So obviously this isn't exactly what's happening, but this is a pretty good picture. So now, what I want to talk about, that's pretty much all I have to say. So hopefully this kind of shows you why first we print out, we come here and print out the numbers 1 through 20, but then we keep calling and we count up to 20, but then after we get done with all these method calls, we have to keep coming back out of those previous method calls and popping stuff off of the stack. So hopefully that made it all fairly clear. And I have one more, just like an analogy that I would like to show you, that hopefully kind of puts this into perspective a little better. The analogy I want to show you is, I think this is a pretty good analogy. I've already recorded this like a million times, and the more I think about it, I think it's a great analogy. Think of each time that we pass in a piece of data and have this method call itself, or even call it initially, we send it one of those little Russian, I think they're called Matryoshka dolls, that kind of looks like a bowling pin, but you get my drift. And so it passes in the data, like all that important data, like the link register and the number 1 in the first call, the case of the first call, it passes in this number 1. And then the second time it calls itself, it sends like another piece of data, which is the number that we originally sent in incremented, and another a new piece of data that tells us what value the link register had when we had this method call itself. And so it does this many times. Those colors don't look that different. And it does this like over and over until we get a giant Russian doll that stores the number 20 and another piece of data for the link register, and it has 19 other dolls inside of it. And so in order to reach those, you have to keep popping them open and popping them off the stack, essentially, which is one of the reasons why I like this analogy, because you have to pop open the Russian doll to get the other dolls, and you have to pop the stack. So that's one reason I like the analogy. But the other reason is that something that I think is kind of poorly laid out in this program is that each time that we have this method call itself, or even call it initially, we don't actually send it anything that lets us modify this variable A. This variable A was never modified at all in this program, and in fact, every time that we called A, or we passed it the new, like, A plus 1, probably should do this in a darker color. Let's do it in blue, I guess. Each A is unique to that method call. So what I mean by this is that I'm going to use the colors that I used here. And so, like, The first time we call it, we pass it A. The second time we call it, we have another A. But these A's are not the same. A equals A plus 1. And then the kind of tealy, turquoisey, green color, A equals blue A plus 1. So let me find, where's that color? I don't even know where it is. Use this one. See, yeah, that's pretty close. A equals A plus 1. So greenish A equals blue A plus 1. And then the orange A is the kind of tealy colored A plus 1 again. So these A's are all unique, and the fact of the fact of the matter is that we actually sent it in 20 different unique pieces of temporary data. Whereas if we had used a regular for loop in here instead of a recursive method, is that it would have sent in the same piece of data each time, and it would have just kept on modifying that same piece of data. Now, you might think that that's kind of bogus because that seems like it wastes more memory than it saves by doing this recursive method, and it's a little more tricky and more dangerous, because if you actually forget this base case, then this program is very fatal, because your stack code will try and overwrite your regular code, which is read-only, and so that causes the program to crash. But it actually produces less code when it's compiled, but that's a different issue. So the underlying thing that I'm trying to say is that each A that we have here is unique to that method call, and that's why I kind of didn't like the fact that I used int A and then called count A, but then called this variable here A as well, because these A's are not really linked. Because the A inside this method is just a copy of this A, and then every time you throw in, you have count call itself over and over. The new int A that you're retrieving is simply a copy of the previous A plus 1, because the other one has been pushed on the stack. So that's kind of a big deal. I'm sorry this video's been really lengthy, but I really felt like my video didn't really do the topic justice after having actually learned more about this topic in at university. And so I hope that I've explained everything pretty thoroughly and well, and not caused more confusion than I cleared up. And if there was no confusion in the first place, then hopefully you just gained a lot of information and didn't get really confused about something. If it was confusing, let me know. I'll erase the video or redo it or put in little annotations or something. And if I rewatch the video while I'm building it, rendering it, then I'll put in some permanent annotations that can actually be seen on like iPhones and iPods or iPads or whatever. So best of luck to you guys. I don't know when I'll be making another video or what. Someone asked me a question. I still answer comments on my videos as much as I can in messages, even though I don't really make videos readily anymore, because I don't know, I just feel like it would be an injustice not to. But hopefully, so I don't know when I'll be making videos again. I'm a really busy person. I may have time this summer if I can find it, but best of luck to you guys, and I'll see you later, I guess.